Okay, so for the first ones here, converting those to hexadecimal. We have to remember our place values for hexadecimal are 16s. So it's 1, 16, 256. The next one would be 4096. We don't need to go that high. So we start out with a 33107. Yeah, let's figure out how many 256s come out of that. So we're going to divide by 256. Helps if I divide instead of multiply. So we get 12.13. 12 in hexadecimal, remember 10 is A, 11 is B, 12 is C. So that's going to be a C there. So now we'll subtract 12 and multiply by 256 to figure out what's left. So there's 35 left. Out of 35, 16 will come out twice with 3 left over for the ones. So C23 is what that is in hexadecimal. How many of you got C23 for that?
I did it for octal.
Oh, gotcha. You switched them around?
I got
C23, perfect. Now 211 base 10 going into binary. So remember, this is the 1s, the 2s, the 4s, the 8s, 16s, 32s, 64s, 128th. The next one would be 256. That's bigger than what we have, so we don't need that. So we'll subtract. Can we get a 128 out of there? You bet. That would leave us with 83. Can we get a 64 out of that? Yep, that would leave us with 19. Can we get a 32 out of there? Nope. Can we get a 16? Yep, subtracting 16 leaves us with 3. Can we get an 8? Nope. 4? Nope. A 2? Yep. Subtracting a 2 leaves us with a 1. So yes, there's a 1. So 1101011 is what that is in binary. Anybody have that one? Okay. Is this making any sense at all to you? Okay. You may have to watch some videos and see what you can catch up. So the octal. So we've got the 1s, the 8s, the 64s, the 512s, and the 4096s. Basically, these place values, you always start with 1. And if it's base 8 or octal, you multiply by 8 at every step. So now I can't get out of 4096. We're not going to worry about that one. 512 comes out of there once. So 99 minus 512 is going to be 487. 64 comes out of 487 7 times. 7 times 64 is what, 448? So now we subtract what's left there is 39. 8 comes out of there 4 times. 4 times 8 is 32, so there's 7 left. So 1747. What do y'all think? Okay. For this one now, we got to remember this is the 1s, the 2s, the 4s, the 8s, 16s, 32s, 64s. That's the 128s, and that's the 256. So there's a 1 in the 256. There's 1 in the 128. There's 1 in the 32. There's 1 in the 2, and there's 1 in the 1. Yep, 419. Perfect. That tells you it's base 2 or binary. So this is telling you it's base 8 or octal. That's base 16 or hexadecimal. So for 8s, this is the 1s, the 8s, and the 64s. So it's going to be 7 times 64, which is, what, 448? And then that's 5 times 8 is 40, and 3 times 1 is 3. Yep, 491. So now then for the hexadecimal, this is the 1s, the 16s, the 256s, and the 4096s. I'm also going to write in F is a 15, A is a 10, C is 12, and E is 14, correct? So this means to convert that, wait till you get your picture. Got her? So to convert that, F is 15 times the 4096. A is 10 times the 256. C is 12 times the 16. And then E is 14 times 1. So I'm just going to punch this all in. 15 times 4096 plus 10 times 256 plus 12 times 16 plus 14. 64,206. Does that make any sense at all? Okay. Converting from the base back into base 10 is a little bit easier to do. Okay. The first thing we want to cover then today is the relationship between hexadecimal, octal, and binary. The only reason octal and hexadecimal exist is because they're just a really handy way to abbreviate binary. If we look at octal numbers, if I want to count up an octal, we've got 1, 2, 3, 4, 5, 6, 7. And we would stop there because at 8, if we're an octal, the largest digit we can have is 7. So the 8 would actually be 1, 0. That's the number 8. Come on. Slide that over here. In binary, 1 is, of course, still 1. 2 is actually 1, 0. 3 is 1, 1. 4 is 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. 8, of course, would be 1, 0, 0, 0, but we don't need to worry about that. We're going to stop at 7. But what I'm going to do is this. I am going to fill in zeros to make those first 3 also 3 full digits. So this is the binary 1, 2, 3, 4, 5, 6, 7. Now that each of those is 3 digits, we can use this relationship, this little key right here, to encode binary into octal, to actually condense it. So let's say I have the binary number like that. I can start at the end of the number. Now each of these is 3 digits, so I'm going to start at the end of the number and go 3 digits at a time. So I'm going to split it there, 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 and there. That's why I started at the end of the number going backwards, because now there's just that 1 there, so I'm just going to fill in 2 zeros to make it a 3-digit number. Any questions on what I've done so far? So what I've done here is I have actually separated the binary number into octal digits. 110 right here can be represented with the octal digit 6. 001 is the octal digit 1. 101 would be 5. 100, 4. 011, 3. And 001, of course, is 1. So the octal number 134516 is an abbreviation for that whole binary string. Yes, it does. Generally what you're doing is you're converting the digital into an analog signal. So then you're sending, rather than sending just a pulse or no pulse, you're sending an analog signal that can have a range. So if it's within this range, it's considered a 0. If it's within this range, it's considered a 1, and so on. I want you guys to encode this into octal then, this binary number. See what you come up with. So let's take a peek. I always start at the right, work my way back to the left. 011, of course, is a binary. So we convert to a 3, the octal 3. 011, still 3. 000, we didn't list that one, but it's just 0. 010, 2. 111, 7, and 011 is 3. So 372033. Any questions on that?
Yeah. For that 10, did that ever come into play or not?
For the 10? No. Because to code a 10, you would need 4 digits.
Okay.
And we're only taking 3 into 1.
Okay.
So you would never have an octal 10 because that requires a second digit for the octal anyway.
Okay.
You wouldn't want to do that. So what if I want to go the other way? What if I want to take octal into binary? So I got to take the code back the other direction. So let's say at 67304. Well, it's exactly the same thing. Binary 4 would be 100. 0 would be 000. 3 011. 7 111, and 6 110. It's that easy. Each octal digit becomes 3 binary. Hexadecimal is just as easy once you have the key written out. So I'm numbering 1 through 16, 1 through F. 1 is 001, 2 is 010, 3 is 011, 4 is 100. I've got to add the 4th digit in front of that. 5 is 0101, 6 is 0110, 7 is 0111, 8 is 1000. 9 is 1001, 10 is 1010, 11 is 1011, 12 is 1100, D is 1101, E is 14 is 1110, and 15 is 1111. So if I want to encode this, let's say I have that binary number. If I'm going to convert it from binary to hexadecimal, I'm taking 4 digits at a time. I'm still starting at the end and working my way backwards. So there's 4, 4, 4, 4, and 4. This one happened to just work out. So I don't have to add any zeros at the beginning. 0, 1, 1, 0 is 6. 1, 1, 1, 1. It's 15 or F. Yep. 1, 1, 0, 1 is D or 13. 0, 0, 0, 1, of course, is 1. And 1, 1, 0, 1 is D again, 13. So D1, DF6 is the hexadecimal coding. So you can see that condenses it even further. That took it from 20 digits down to 5. Better? Going the other direction, so FACE2. We're going to do the same thing. 2 is what? 0, 0, 1, 0. E, 1, 1, 1, 0. C, 1, 1, 0, 0. A, 1, 0, 1, 0. And F, 1, 1, 1, 1. So the converting from binary to hex and binary to octal, all you gotta do is write out the key, and it's really simple, really quick. And that's why they use it. It's just a way of condensing it. So instead of having to send 20 pulses here, you can send an analog signal that contains 5 pieces of information. And as efficient as digital is, sometimes it is more efficient to send an analog signal with less packets. Okay, we're going to look at some operations. We're adding numbers. Now remember, for binary, that should be as far as we have to go. 1 in base, this is base 10, and this is binary, base 2. 2 is 1, 0 in binary. So it doesn't take much to have to carry in binary. So if I simply have 1, 1, 0, 1, 1 plus 1, 0, 1, 1, 1. Well, 1 plus 1 is 2. Remember, 2 is 1, 0. So I'm going to keep the 0 and carry the 1. 1 plus 1 plus 1 is 3. Remember, 3 is 1, 1. So I'm going to keep the 1 and carry the 1. 1 and 1 is 2, which is 0, carry the 1. 1 plus 1 is 2, so 0, carry the 1. 1, 1, 1 is 3, so 1, carry the 1. Now, I went kind of fast there. For where? For the 3? No, 3 is just 1, 1. I put the 0 here for the 2, and then I carried the 1. So let's add these two. You guys walk me through it now. 1 plus 1 is? So 0, carry the 1, yep. 2, so 0, carry the 1. So 3, so 1, carry the 1. 2, so 0, carry the 1. 3, so 1, carry the 1. 2, so 0, carry the 1. 1, 1. Not so bad? Okay. Now, I'm going to show you something that we sometimes miss when we're dealing with our base 10 numbers. if I have to add, I don't know if I can even write enough of them out here. Six, 7, 8, 9, 10, 11. I get one more in there. So if we're adding up, this is 12 numbers here. If I'm adding these up, I've got 9 plus 9 plus 9 plus 9 plus 9. It comes out to 108. Obviously, we're going to keep the 8. Do we carry the 10? What we can do is this. We carry that 10, but I can put the 0 here and the 1 over in this column. Now, we don't have any numbers here, but that 1 will be here. Now, that doesn't mean there isn't going to be more carried from here yet, because there is. We've got 0, 3, 5, 13, 14, 17, 21, 27, 34, 38, 44, 49. So it's going to be 9 carry the 4 yet. So 4 and 1 makes 5, 519. So we could have put the 10 here and added the 10 down and carried a 5. But we can carry the 1 and then keep carrying more on top of it. The reason I'm showing you that is when we deal with binary, this happens a lot.
So it wouldn't make a difference for the way it adds out?
Doesn't make a difference whether you carry the 1 and leave it there. You may have to still carry and add to that 1 with your other carry. Or you could add 10, and when you get to the bottom, it's going to be 59 instead of 49. So
it doesn't make a difference?
Doesn't make any difference, no. But most people don't realize that you can carry multiple columns at once, multiple place values. You can actually carry from one column. Like if that came out to be a 13, if it came out to be a 13 at the bottom here, or let's say it's 135 or something like that. You can put the 5 here, you can carry the 3 into this column and the 1 over into the next column. That you can actually carry more than one column over. Or you could just carry the 13 and add it down through. So if we're dealing with binary numbers, like this, so we've got 1, 0, 1 is 2, so that's 0, carry the 1. 1, 1, 1 is 4, which is 0, carry the 0 and the 1. Does that make sense? Yeah. So we kept the last at 0, then we carried the 0 into the next column and the 1 into the second column over. So we got 0, 1, 1, that's just 1. 1, 1, 1 is 4 again, which is, so we're going to keep the last 0, carry the next 0, and carry the 1. 0, 0, 1 is just 1. 1, 1 is 3, so that's 1, carry the 1. That's 4, so 0, 0, 1. Now, I didn't have any here where I had a second carry on top of it, so let's do another example where we run into that.
So it just has things that you just put that through as a normal. Or you just add that to your
Yep, here I'll show you. So here we've got 2, right? So 0, carry the 1. That's 4, so 0, we'll carry a 0 and a 1. Here we've got a 3, which is 1, carry the 1. So now we've got 2 1s up there that are carried. So we've got 1, 1 is 2, 3, 4, 5, which is 1, carry the 0 and the 1. So here we've got just 1. This is 3, so 1, carry the 1, and 4, so 0, 0, 0, 0, 1 again.
If you ended up with like a 6, would you have done something really wrong? Or...
Well, with 3 digits, the highest number I can come up with is a 5, generally. But yeah, 6 then would be 1, 1, 0. 7 would be 1, 1, 1. It all depends. You can come up with a 6 if you're adding, 4 or 5 numbers.
Yeah.
You can come up with a 6, you can come up with an 8. That's weird because at 8, of course, it's 1, 0, 0, 0. So if you're adding 6 or 7 numbers together, you can come up with an 8. So then you got to carry the first column, the second column, and the third column, which is kind of weird. Or what we could have done here, get a calculator as binary. There are apps out there, yes. Okay, so we got 2, so this is 0, carry the 1. This is 4. So now what we're taking out of this 4, we're keeping 2 and we're carrying 2. So you can actually do it like that. You can carry the 2 instead of making it a 0, 1. It's still going to work out the same. This is going to be 5.
I'm sorry, I didn't see what you did.
Well, when I carried here, I kept the 0, which is a 2. Because its base 2 is 0 is worth 2. A base 10 is 0 is worth 10. So I kept the 0, which is a 2. So 4 minus 2 is 2. So I carried the 2. And I do the same with 5. I've got a 1 to keep there. So I'm taking out 2. I'm carrying. Oops, I'm only carrying 2. I kept a 1 and then another 2. To me, this is more confusing because trying to figure out what am I carrying, a 1, a 2, or a 3, it's a lot more confusing to me. To me, it's easier to carry the 0 and then the 1 into the second column. So I don't like trying to do it this way. So technically what you're doing here, like with the 4, you keep a 0, so you're carrying all 4 of it. You lose 2 when you move over a column. Here you had 5, so you're going to put 1 there. So you've got 4 left. You lose 2 when you move over a column. Again, to me, that's really confusing. I'd rather just carry the 0s and the 1s and go multiple columns. Sure. I'm going to take this off here though, so you don't see that in your picture. What if we wanted to subtract in binary? What's that? Find the app. Not a bad answer. Well, of course, 1 minus 1 is 0. 1 minus 0 is 1. There's nothing difficult there yet. Here, though, 0 minus 1 can do. So we got borrow. Well, borrow from this one makes that a 0. What did I borrow? 2. Each place value goes up by 2. It's base 2, so I borrowed, like base 10, you're borrowing 10. Base 2, you're borrowing 2. 2 minus 1 is 1. 0 minus 0 is 0. 1 minus 1 is 0. So this is just 1, 1, 0, which is 6. Yeah, those don't mean anything. They're just, I mean, if you're encoding in a computer, you have to have those 0s there for placeholders because you have so many bits you've got to fill. But if you're just doing them up by hand, you don't need those 0s there. Okay, so we're subtracting here. 0 minus 1 can't be done, so we got to borrow. This becomes 0. This is going to become 2. 2 minus 1 is 1. 0 minus 1, we're going to borrow again. This will be 0, and this becomes 2. 2 minus 1 is 1. 0 minus 0 is 0. 1 minus 1 is 0. 1 minus 1, or 0 minus 1 can't be done. Nothing to borrow from here. So this is a 0. This becomes a 2. I'm going to borrow again. This becomes a 1, and this now becomes a 2. So 2 minus 1 is 1. 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 1 is 0. So is that like a 19? Let's just do this. What if we want to add in hexadecimal? Personally, I cheat and I look them up. We know A is 10, right? So I'm going to replace A with 10. B is 11, so I'm going to replace B with 11. C is 12, there's no C. D is 13. E is 14. F is 15. So I just usually write those in like that. So I have it. And now my adding is no more difficult. Remember, the largest digit we can have is a 15, which is an F. So 4 plus 7 is what? 11, which encodes to be a B. 13 plus 10? 23. Now, I have to carry 1 from that because it's bigger than 15. What I'm going to take out of it, this is base what? 16. So I'm going to take out 16, which is going to leave me with 7. 23 minus 16 is 7. So I've got 1 and 10 is 11, plus another 11 is a 22. So again, that's bigger than 15. I have to carry 1. I'm taking out 16, which leaves me with 6. So this is 16, 19. Again, I'm going to carry 1, leaving me with 3, and there's my 1 I carried. So 1367B. So I do the same thing here. I'm going to cheat and fill in. A is 10, B is 11, C is 12, D is 13, E is 14, both times it appears. And now 17, so I'm going to carry the 1, leaves me with 1. The 17 minus 16, right? The one I carried took out 16. So I've got 26 here now. So I'm going to carry 1. What am I going to keep? 10, which is an A. This adds up to 25. So I carry 1 and I keep 9. And that adds up to 21. So I carry 1 and I keep 5. So 159A1. We having fun yet? It's actually kind of interesting. It's the hexadecimal, the binary addition subtraction, yeah, there are applications for it. The hexadecimal, it doesn't. Most of the time they convert it into binary and do it that way.
So it's not really used except for really high-end stuff.
Yeah. There is that. Oh yeah, I know what you're saying. Let's say we're going to subtract. So put in 10. C is 12. D is 13. E is 14. F is 15. So we're going to have to borrow. 3 minus 13 can't be done. So we borrow from this. It's a 12. What's this become? We borrowed 16. So plus 3 is 19. So 19 minus 13 is 6. 12 minus 14, we got to borrow. So this will become 13. This is going to become 28. We had to add 16 to it. Minus 14 is 14, which is E. 13 minus 12 is 1. And 15 minus 10 is 5. 5, 1, E6. Okay, so in your packet, you got the page 503, 507, 511, 515, and 517. Just look through the odds. I mean, we've done the first part of a few of those. Look through the odds converting between octal and binary and hexadecimal and binary, and then there's some with binary and hexadecimal addition and subtraction. And that is it for the test tomorrow. I'll let you guys have the last few minutes to get started if you